Hey Sam,
Hi Sam.
we're back. New battery.
I just threatened everybody. Okay, so we're going to combine these two equations here to find, because we know the force of the thing orbiting is equal to the electrostatic force. So we'll do.
So when I'm doing the orbit, you just do F equals F. So mv squared r equals the other one.
And the radiuses cancel out. One of them.
Yes. So what can we cancel? Well, we can cancel out a radius. Anything else? Nope.
Since it says speed, do we not have to have a vector?
If it says speed, you do not have to have a vector. We're solving for what? The speed. So we're going to solve for velocity here. So I'm going to leave it as v squared until we do all the math. So k q1 q2 divided by 1 radius times the mass. Okay.
Just so nice. Will we get points off if we add a vector that's not really supposed to be there?
Not for speed, but it's hard to say a vector for orbiting.
Yeah, but like if it's traveling.
If it's pot now, I'll never take off for
In a
a
circle.
sensible vector.
No.
Alright. So tell me, Matt, tell me how to fill this in so I don't have to look.
You just
So
put it all
K,
in.
What's K?
9.0 times 10 to the 9 Newton. Yeah, that one.
That. And what are my charges?
We have plus or positive 1.6 times 10 to the negative 19.
That's so weird to say. Coulomb.
Coulomb. That ends in a B.
And it's,
Oh.
and the other one's the same thing except for it's
Yeah.
negative charge.
Is it?
Coulomb.
Yeah, it says. And
Mary had a little lamb.
Charge of negative 1.6 times 10 to the negative 19.
The Holy Lamb.
What's a helium nucleus?
Oh,
2 protons. So my negative charge would be 1.6 times 10 to the negative 19. Because I have 1 electron, but I have 2 protons. So what's my net charge in the nucleus?
would you just double it?
Double it. Is that bubbled? Oh my gosh. Yeah. Okay.
Oh my gosh.
And the radius?
Is
I thought it was my phone for a second. I was like,
5.29 times 10 to the negative 11 meters.
And the mass?
It is 9.1 times 10 to the negative 31st kilogram. Did you put the 31?
Negative 31. Do I want kilograms?
Yes.
Yeah.
Okay.
It's a tiny
Because then-
kilogram.
Okay. So, everyone plug and chug and get me an answer. Remember to take the square root of the answer once you get it.
3.1 times 10 to the 6 meters per second.
Three point one times 10 to the 6 meters per second. That's what I get. Alright, so we know.
So that means you could put 1.098901099 times 10 to the 30th of these little protons in a kilogram.
Wow.
I don't know why it wouldn't be the same. Like, why you wouldn't just take just say 9.1 times 10 to the 31.
Didn't I just say 9.1 times 10 to the 31?
No, I mean, like, when you're saying how many of them are in the kilogram, wouldn't it just, I
Oh,
don't
because
know.
there are electrons in the kilogram too. And air.
Well, no, I mean, like, I just took that number, 9.1 times 10 to the negative 31, and I divided 1 by that number, and it comes up with this number.
Right, but in a kilogram of stuff, there's more than just protons.
No, like, just numbers. Just numbers. 1 divided by that number doesn't equal the opposite of that number.
And that's
Oh, wait, no, that's because it's 9. It's got, like, 9, so it's like dividing 1 by 9 or something. I don't know. Never mind.
I'm too out of
Never
it
mind.
today to understand anything. Okay. But anyhow, we found a velocity. Now, we're gonna play with some angles just to make sure we can all do this. So positive, a negative, and a positive. Okay. So let's look at a hypothetical situation for one of those horrible sine cosine problems. Alright, so here's my positive x-axis, positively charged particle. Let's say I have a negatively charged particle here and a positively charged particle here. Okay? So, I have to make up some angles now.
Is this the extra practice problem?
No, this is just something I'm making up at the moment.
Okay.
So, there's no right answer at this point. Let's say this is 30 degrees, and let me make this a weirder angle than that so that we have more complexity. So, let's say this is 10 degrees. Okay, so, if you consider these separately, okay, this positive particle is going to start traveling. Okay, it will be attracted or repelled to this negative particle.
Attracted.
It'll be attracted, so it's going to move in this direction, right?
Mm-hmm.
So you measure the direction it's going to move, assuming this is a nice straight line, which it isn't at the moment, relative to the positive x-axis.
But won't it also be repelled by the other plot?
It will, but consider each of them separately, right? So, in what direction relative to the positive x-axis is it going to travel?
170.
170 degrees. Okay, now will it be attracted or repelled by this positive guy?
Repelled.
Repelled, so it's going to travel in this direction, right? So we know that equal angles here, right? Some math theorem somewhere tells us that. So along what direction will it travel but when it's repelled by that guy?
210.
Right, 180 plus 30 is 210. So when you do this, you're going to break it out into this, right? X. And you're going to use the cosine and sine of 170, cosine and sine of 210 for this problem. Okay, the hardest part of that test is figuring out what angle to use. So you have to think, is it being attracted or repelled? Where is it going to travel? Use that angle from the positive x-axis to the line along which it will travel. Positive x-axis to the line along which it will travel for each particle that's interacting with it. And there are only 2 on the test question. It's not like they give you like 3 or some crazy thing. That would be really mean. So, what do we want to think about other than that? I don't think there's anything hugely that I want to think about. Very similar to the practice problems other than that one crazy one. So, let's try a few interesting things lab-wise. Last week we talked about electroscopes. You had to write an electroscope lab. Did anyone write it? Righto. Excellent.
It wasn't here.
Since there's no like math, you can feel free to type it up and email it.
13.2.
What in the world was that?
13.2, that's it.
13.2.
Let's look at what you should have written.
We only have one more lab.
The capacitor lab, and then you'll have lab activities with like worksheets and such things. But yeah, you're almost done.
Stop.
I have like
So,
Listen, guys,
I'm going to try to do it and see if we're drier today, yes?
is everybody all updated? So if you went on there, can you see like what labs we have in there yet?
Yes, it should be. Other than what you turned in today and or anything I've forgotten to do.
Pay attention, Sam.
Yeah. As if last week's videos weren't bad enough. Alright, will you make me a couple of little foils to hang off of there? While I So we're gonna redo this just to see if we can get anything to work, and then we're gonna try a couple of things I've never tried before for the fun of it. But at least we'll have a discussion, since you guys have probably already forgotten what you should write your lab report about since you didn't write it. Alright.
I remember it.
This is just like those little men that you.
Yes.
That you.
Oh yeah, the
Stuff
Wooly
on?
Willy or something.
Yeah.
What are they
The
called?
mustache
Bullet
thing.
pine? No.
But the beauty of it is you can
Oh, there
actually
used to be-
see.
There used to be
Okay,
a-
remember how we talked about light, and we talked about how light is electromagnetic radiation, and it's a transverse wave where it oscillates perpendicular to the direction of its propagation, right? But electromagnetic radiation has the electrical part that oscillates perpendicular and the magnetic part that oscillates in the other perpendicular direction to its direction of propagation. So electric fields should be visible. You have a complete circuit and you dump a bunch of magnetic stuff around it because electrical circuits are electromagnetic radiation. They have that electromagnetic field. That's what we're going to try to do with that stuff today. I don't know how that's
It's
going
like
to
it's
go,
alive, like you're not touching it.
but we shall see. What in the world is going on? Okay.
That's Magnet
So-
Sam.
Whoa.
First thing we do
Whoa. How are you doing?
is. Alright.
Alright, pay attention to this, Sam.
Alright. So I didn't condition. They're really close to each other. So when I just charge this up and bring it near. Oh man, I touched it. Maybe I want this a little higher. A little higher. Beautiful. Okay. I wish I had like a Van de Graaff generator so I could have all the charge I want without being ridiculous.
My mom, whenever she's doing experiments for her class, she always comes up and uses my hair.
Alright, so you saw them jump really nicely, right?
Mm-hmm.
Okay, so what happened in this case?
They were a different charge.
The negative particles got pushed away. Like the negative that were in the
So
paperclip got pushed down into the aluminum, and so they both
both
got
the same
negative and
charge.
pushed away from each other.
Okay,
Really?
so electrons always repel from a negative charge. The negatively charged balloon came near, it made all the electrons run away to try to get far as they can from the negatively charged balloon. So they moved as far down as they could. But that made a greater negative area of charge in the bottoms of the foil, so they also wanted to get away from each other and repelled each other. Now, they should not have gotten a permanent sort of charge because I didn't actually add any electrons to the system. I just, oh look, the foil is like being attracted. It doesn't matter if I'm touching it or not. Huh, weird. Something just flew across my room. Okay, so if I touch the loop with this negative charge here, then what will happen?
Not much.
They'll flow freely and then.
Look, something is happening. Okay, so electrons flow from this concentrated Josh area of electrons on the balloon to the less concentrated area. They're packed in here. They want to get away from each other. Even though there'll be too many electrons, they can get away from each other to some extent by spreading themselves over throughout there. So the foils contain more electrons than protons, hopefully, at the moment. So they're repelling each other. If I touch, they should move back together a bit. I don't know if that actually happened. It's so hard to tell. So I'm charging
Gosh, it's
by,
working way better than it did last
yeah,
week.
induction or conduction here.
Yeah, we did this last week.
Conduction.
Yeah.
Oh, I'm charging by conduction because I'm actually touching.
It was so charged,
When
it
you
was
charge
pushed all the way away.
by conduction, you impart the same charge to the thing that the thing you're charging with has. So since I have a negatively charged balloon and I touch the loop, I'm imparting a negative charge to the electroscope.
Should you put the ends closer together?
Yes, that would be good. I would just like it to stay on the electroscope at the moment. You know, I'm thinking it's worth buying a real electroscope for this lab. This is really annoying and not very functional.
We should do it the way he does it. Like you get like a glass or something, then put the lid over that.
Yeah, well, we did that the first year, but when you do that, you just end up with the things falling off and then you have to fish them out of the glass every time.
Mm.
Oh, sorry, Sam. Alright, so they're kind of close to each other. Alright. So now I'm going to try to charge by induction, which means that I'm going to try to impart a positive charge on the electroscope. So I will touch, allowing the electrons to get away. I'll bring this near to try to repel electrons away from the electroscope and drop the foil, of course. Gotta love it.
Well, that shows that it's being repelled.
Did it?
It was repelled all the way to the ground.
Yeah, it flew right off because it was being repelled so strongly. Maybe that's it too. Wouldn't that be nice?
Ain't that neat?
No, it's frustrating. Okay. Electrons will leave the electroscope. I wonder if it is doing that because
I think it is. I mean, it only happens when you do that.
oh, I touched the metal. So frustrating. Okay, finger touches, bring near, electrons, make it, send electrons away from the electroscope out through my finger. Then we take them away. The two foils hopefully should be repelling because they have a positive charge because electrons got away. If I touch, they should move closer. Oh, they did move closer to each other. Did you see that?
Yeah.
It worked. Here, I'll turn it. You want to be looking kind of sideways at it. Okay, they're not touching at the moment. So put on finger, bring near. Electrons run away. Take them both away.
Why didn't it work last week?
Because it was too humid.
It worked.
It worked.
She wasn't here.
Oh, it was worth fumbling around with that to actually get it to work. Hooray. I feel so much better about it.
Amish County,
You were.
Now.
Lancaster, Pennsylvania, or Mennonite. Is it
Oh, yes.
Mennonite?
But humidity wrecks static electricity experiments. So now,
Hey, you want some Cheerios?
we're going to try a few weird things.
Oh.
I'm hoping that a circuit here Alright, so I'm going to go from positive to negative. That might actually be a complete circuit, right? Where's the end of my wire's like all messed up. And there's a zip tie on it.
So what
Right,
happens if you
sugar
just connect it like that? Like if you connected the two both terminals of the batteries, would it just like switch it so like give the Duracell's charge to the BJ's charge and the BJ's charge to the Duracell's charge?
Yeah, but it'll have resistance through the wire, so it's gonna waste, like friction. Waste charge, basically.
So if you did that for a while, it eventually just killed both batteries?
Yes.
Oh my goodness.
Okay,
When we put
so
it in the water last year and I got shocked.
how could you get shocked from a tiny D battery? I
It
just don't
did shock.
understand.
It shocked.
Do not understand.
It was like,
Do
you
not
could feel, you
understand.
put your finger in there and it was like,
Alright, here's where.
Do you know how to
common
test
sense
if those
is, like,
are still
so
live?
important.
Put them on your tongue.
Yeah, let's don't. We'll assume.
it feels good. Shit.
I never
So-
understood how it worked. Like I'd put it on my tongue.
From
and be like,
positive, where's my negative?
My brothers were so
Negative.
stupid, and they'd be like, "This one's dead. This one's not."
Okay.
So you lick them both?
So I'm gonna drop everything 600 times. Let's do it with the batteries just laying down. That'll work.
What's happening?
No. This will be a complete circuit with 9-volt batteries, so I'm gonna hopefully.
Are they alive batteries?
One would hope. Okay. So, scooting them backward. Alright, so hopefully we have electromagnetic radiation flowing here. And
How do you know?
we don't know. I'm gonna disconnect for a second. And I'm gonna try poking a hole in this piece of paper here.
Well,
I know, right? And running this through here
So Josh,
like this.
since you can test a 9-volt battery with your tongue, that means you could probably test a 12-volt battery with your tongue, right?
oh, I would probably die.
We are not testing
What,
any
car
batteries
battery?
with our tongue today.
Car battery is only 12 volts. Why can't you test that with your tongue?
I
Because
would
you're not.
die.
Why? It's only 3 more volts.
We'll learn about that in module 15. Don't listen to these
Didn't we
people.
learn about
Well,
that in
Josh, you're
chemistry?
crazy.
Maybe a little bit.
I've seen videos of people doing the jumpers wrong and getting shocked.
Oh,
Reversing them?
gross. So I'm hoping we'll see
Reversing.
electromagnetic field lines.
Positive to
But I'm not
negative.
sure how that's going to work out.
Wait, where did this go?
You let it rock itself.
So what's the point of doing
I've seen
that?
people
I
put
have
it
no
idea.
together and spark it.
I'm just trying
Oh
to
yeah,
see field
my
lines.
scout leader did that. He was like, when he had to jump the battery once, and he was like, "Okay, guys, see this? Don't ever do this." And he's like,
Oh, just like kick sparks with them. I wonder.
You know, I like them putting tinfoil instead of toilet cleaner.
Oh,
Because it makes a bomb. But
that's not doing anything. I was hoping it would do something, but.
I haven't done it, my friend did, and it was scary.
Alright, well, that's not
Everywhere.
hard.
You put it inside of a
I
bottle,
just spelled it out.
tinfoil. and
Alright,
then
well
toilet cleaner,
here,
And then put the lid on, shake it.
hopefully,
And it's just like,
alright, we have to move these, so try not to get shocked when it's, oh, it's not hooked up, that's why.
both your arms.
One of these came unhooked as I
It's a
shock
tinfoil
myself.
reaction, but it's just a
And
bad-
how do you-
the same scout leader wrote his name in letters of fire in the air. He
Kinda
found this old can of like coffee creamer, like the powder stuff, and like shook out
Okay.
the stuff in the
Here.
air.
Everybody
and it, like, floated
grab
there
a
and inflated his
compass.
lighter.
Good grabbing. Here. Guys, you'll have to get a compass passed to you from a
But
friend.
the magnets will
Alright.
affect it.
Awesome.
Well, this
that.
shouldn't be magnetic now, and I'm hopefully
Right.
cleaning this up over here.
What we have to do?
So
Okay.
come over and make a loop with the circuit, and everybody place your
I am
magnet.
facing due southwest.
Turn off that thing, and we'll show Sam at the end. This will just
Okay.
waste